How to build a high linearity, high speed analog optoisolator using the HCNR200 and 201. This is a pretty cool but very simple chip. It basically consists of just 3 parts, one LED and a matched pair of photodiodes. These are very closely matched, so you can measure one photodiode and then have a proxy for what the output photodiode is doing without actually having contact to it. And the high accuracy comes from the very close matching of the two photodiodes, with the currents of them deviating by only +15 for the 200 and +5% for the 201. And from there, both photodiodes are very linear over the photon flux input. This is mostly just a scaling factor that you can compensate out. Let's review some basics. First of all, let's go over photodiodes. Here we see the IV curve of a photodiode. You can see with P0, where no photon flux is applied, behaves mostly like a normal diode with a conduction phase in the positive region, a reverse blocking phase, and then a breakdown phase. However, if we apply an increased photon flux to the photodiode, we can see there is a reverse conduction happening to a specific current, IP, which is very proportional to the actual photon flux coming in. This makes photodiodes very good for measuring light levels accurately. We will be utilizing this effect. So we will be reverse biasing the diode and seeing what photocurrent flows backwards through it. Okay, so let's quickly go over how op-amps work. An op-amp has 2 inputs, the positive and the negative. They're called the non-inverting and the inverting input, and they produce an output. If the positive input is bigger than the negative input, the output will rise. If the negative input is bigger than the positive input, the output will fall. Usually, op-amps are configured in a feedback configuration that keeps the 2 inputs at the same level. You can see here where the feedback is happening with a resistor, or here where the feedback is indirect through the LED and then over to the photodiode. Let's first focus on this section. We know the op-amp is trying to keep these 2 inputs at the same potential, so we can see there's 0 voltage over the photodiode. If we look at the chart and we look at the 0 voltage line, we know we will have to be here. As there is right now also 0 current, the diode is completely off, 0 voltage, 0 current. And these connections are at the same potential, and we call this a virtual short, as both are on the same potential, so that we can assume this to work kind of like ground. If we now have an input voltage going through a resistor to ground, we then have a current flowing through there. In this case, let's assume this current to be 10 microamps. So we'll have this current flowing in here to this virtual ground potential, and from there it increases the voltage as it can't flow any further. So the negative side is larger than the positive side. This means the output will go down, and we can see the LED is connected to the voltage with the other side connected to the output. So as the output goes down, more current is flowing through this LED, increasing the photon flux on this photodiode until it becomes more and more conductive. So we move down as the photocurrent applies and the current increases, until at some point the current matches the current that we inputted into the system. So now we have 10 microamps flowing through this resistor into here and through the photodiode, so that the potential over the photodiode becomes 0 again. This type of transimpedance amplifier is called the zeroing type because of this. We can have any number of currents flowing into this node, and it will activate the LED however strong it has to, so all these currents also flow through the photodiode. As we have transformed the voltage into a current, this is a class of transimpedance amplifier, meaning it turns current into voltage or voltage into current. So now we have a current flowing through this photodiode. So let's look at how this diode behaves. Right now there is photon flux being applied to it, equal to the one applied to this diode. So we can look at the P1 line with current being 0. So there will be a positive voltage applied across the diode. So now we see the diode has a positive voltage. This side has a higher potential than this side. So the positive input is larger than the negative input. This increases the output and lets a current flow through this resistor into this node. This will keep keep increasing until current flowing through this resistor matches the 10 microamps the other diode is having. At the 10 microamps level, the voltage will be back to 0, so the output will not further increase. This has transformed the current flowing through the photodiode back into a voltage, and by choosing this resistor to be equal to this resistor, we have transformed it back 1-to-1 into the original voltage. If we change the ratio of this resistor to this resistor, we can have different gains. This is the basic topology. So let's now look at the practical topology. So here we have a few more components that we didn't have in the simplified version. Let's first look at the input side. We have a new resistor R3 here in series with the LED. This makes sure the LED cannot burn out if the input here tries to draw too much current. We can see from the datasheet that the LED can have a maximum continuous current of 20 milliamps. And a peak pulse current of 35 milliamps, but we should still choose this resistor to be compliant with the 20 milliamps so we do not accidentally burn up the LED. So we can find this pretty easily. We can assume about a 1 volt drop over the LED. So we just take the supply voltage minus 1 volt and then calculate the resistance required to get this current. So here we have 5 volt minus 1 volt makes 4 volt. So we have 4 volt and we want 20 milliampere. So we will have to choose 200 ohms to achieve this. Then R1 and R2 are similar to the previous design. We now have also C1 and C2. These are basically low pass filtering capacitors to make sure these op-amps do not start oscillating at high frequencies. We can see this experimentally later and find good values to give us maximal bandwidth with minimal oscillation. So here we have built up the circuit we just described, the optical isolator in the middle, separating it into the input side and the output side, 2 op-amps. Here is the input voltage, here's the output voltage. You have the input series resistor right here, as well as the LED current limiting resistor right here. And this is just a 50 ohm resistor over the input to match the signal generator output. Here we have the feedback resistor on the output side, well as here is the output side capacitor on the feedback path, and here's the capacitor on the input side. At the top we have power rails separated in the middle with bridgeable jumpers. We have the input power rail with a bulk capacitor and a decoupling capacitor, as well as a bulk capacitor on the output rail, as well as a decoupling capacitor near the device. We will now attach an input signal to the input port. We have now added a bit of instrumentation. We're injecting power into the 5 volt and 3.3 side from the lab power supply from isolated power rails. We are injecting an input signal from a Y splitter on channel 1 going to the back to the arbitrary function generator, and channel 2 is connected to the output of this board. We also have a probe for probing the output of the first op-amp. On the oscilloscope we can see on channel 1 the input signal with a range from 0 to 5 volt, and on channel 2 the output signal with a range from 0 to 3.3 volts. We can see that even at 100 kilohertz these signals are still very well behaved. We can see with the ramp that this is reasonably linear. There are small bumps at the extremes, but this can be tweaked with the capacitor value. Let's now look at some common faults of this circuit. Let's first look at R3, the LED current limiting resistor. If R3 is too big, the LED cannot fully turn on, so we will get clipping at the upper end of the input range. R3 being too small poses a much more subtle problem, however. This was let too much current flow through the LED, potentially damaging it. While peak currents of up to 35 milliamperes are allowed, this does pose a risk of damaging the diode. In normal operation, the LED current should not be excessive as it is regulated by the op-amp. However, during abnormal states like turning on, it might be pulled to one of the extremes for prolonged periods of time, burning up the LED. A similar thing can happen if the input series resistance is chosen to be too small, and too large of a current is being inputted and the photodiode cannot match this current effectively. The input current should not exceed the recommended 50 microamps. If the resistor chosen is too large, only a small part of the 0 to 50 microamp range is used, effectively reducing resolution. If the value of the feedback capacitors is chosen to be too large, this will add a low-pass filtering effect to the circuit. If they are too small, however, the op-amps might oscillate. In this circuit I chose 2 picofarads as this gave maximum bandwidth while stopping oscillations. If your signal has a lower bandwidth, it might be a good idea to reduce the bandwidth further to not amplify any noise. There exists a small discontinuity when the diode turns off completely, leading to a small bit of distortion at the very low end of the signal. This can be fixed by adding a small offset voltage to the input or adding additional currents as described in the bipolar configuration. The small current flowing through the diode in addition to the input signal leads to the diode not fully turning off even when the input signal is 0. And since the same current can be applied to the secondary side also, this cancels out. Make sure to use high quality resistors, as otherwise it might introduce an offset voltage at the output that needs to be calibrated out. With a larger bias current, we can also have full bidirectional operation by shifting the 0 point to the middle of the range. This however means that you also need negative rails on your op-amps. Like and leave a comment if you feel like this helped you. You can also reach out if you need help with your engineering projects. Contact info in the description.